Hey guys, today we're going to talk about the basics of Boolean algebra. We're going to be going through the beginning rules, the first 19 rules of Boolean algebra. We'll apply those theorems to a couple of example problems, and we'll also talk about how they relate to the gate logic that we've used up until this point. Now, there are more theorems that we haven't addressed in class yet, but we'll get to those at a later video. All right, let's go ahead and get started here. So these are the first 19 rules of Boolean algebra, and at first glance they can look really confusing. First off, we've got some math symbols that we've seen in a traditional math class, but remember that those have different meanings in Boolean algebra and with digital logic. So any place where you see a multiplication symbol in this table does not mean multiplication, and any place that you see a plus sign in these logic expressions, they don't mean plus. So remember that any place you see that dot, that means and any place you see a plus, it means or. And we'll be helping to understand these by applying them to and or gates as we work through these. So let's first look at the first four principles, the first four theorems that we see in this table. So the first one says x and 0 equals 0. The second one says x and 1 equals x. The third one says x and x equals x. And the fourth one says x and not x, that's what that line above the symbol means, equals 0. So if we take a look at this AND gate here, we can apply this and help our understanding. So let's say that we have an input x and we have an input y and we have an output that we'll just call f. By definition, an AND gate requires that both x and y are 1 in order to create an output of 1. So we can use this to create a basic truth table with x and y and f. And we can do that by applying our standard inputs of 0, 1, 0, 1, and 0, 0, 1, 1. So there's our table, as cursed as it looks. 0, 0, 1, 1, 0, 1, 0, 1. So in this truth table, and we can check it on the gate here as well, the only time that I can get an output of 1 is if both x and y are both 1. Everything else gives me a 0. So it doesn't matter what, the only time that I get an output of 1 is if y equals 1. X can either be 1 or 0, but it only matters if y equals 1 too. So that means that any time that x equals 0, I get, out of an AND gate, I get equals 0 from my output. And we can see that play out over here in our Boolean expressions, the first four rules. So if y is 0, it doesn't matter what x is, I get 0. If y is 1, my output is going to be whatever x was. If x was 1, then I get 1. If x was 0, I get 0. The third one says x and x equals x. So if both of my inputs are set to 1, in this case that means they're both equal to what x is, right? Then the output matches. But if they're both 0, I still get 0. Okay, number 4 is kind of like the definition of an inverter gate, right? If I take an input and I invert it, no matter what I do, I will always get 0. As an example, let's say that x is equal to 1 at the input, and then I run it through an inverter. That means now it's 0. So 1 and 0 gives 0. They have to both be 1 in order to get a 1 out, right? If x is 0, that means the inverter turns it into a 1. So either way, I get 0. So we can use AND to explain the first four. We can use an OR gate to explain the next four. So the next four are x or 0 equals x or 1 equals 1, x or x equals x, and x or not x equals 1. So an OR gate's truth table is true if one or the other is equal to 1, or both. So our truth table here, 0, 1, 0, 1, 0, 0, 1, 1. There's x, there's y. Let's put our output over here. I'll try to make this a little bit cleaner this time. There's our table. So my output when x and y are both 0 gives me 0 because neither of them are 1. I get a 1 if y is 1 and x is 0. I get a 1 if x is 0 and y is 1. And I get a 1 if both of them are equal to 1. So this is kind of like the opposite of an AND gate, right? So if we take that and we apply that over here to the next set of theorems, x or 0 equals x. So if x is 1, then the output is 1. If x is 0, then the output's still 0. Number 6 says x or 1 equals 1. If y equals 1, it doesn't matter what x is, because the OR gate is satisfied if one of them is equal to 1. So if we OR 1 to something, we override and it just equals 1. That one's pretty important. Number 7 says x or x equals x, which means that if both of my inputs are equal to each other, if they're both equal to 1, then they could both equal 1 in the output. If they're both equal to 0, I'm still going to get 0 out. Number 8 is kind of like the OR version of theorem 4, which is that it says x or not x equals 1. Now with theorem 4, x and not x equaled 0 because that means that one of them is 0, and in order for an AND gate to give 1, you have to have 1 and 1, right? But for an OR gate, if one of them equals 1, then the output is 1. So with x or not x, one of those is a 1, and one of those is a 0. So either way, the gate's going to output a 1. Okay, so number 9 is a little bit different. This is a double inverted theorem. So this tells us that if we invert something twice, we will get the original back. This is kind of like squaring a square root, right? We're kind of canceling out that inversion, or taking the negative of a negative number in real math, right? So if I have x equals 1, and then I invert it, I get 0. If I invert it again, I get 1. So that's the double inversion theorem. Okay, so the next 13 principles here, the theorems that we see, are essentially what I like to refer to as the math works principles. So the first one, number 10, tells us that we can apply ands in whatever order we want. So you can see that it says x and y equals y and x. It means that we can put the letters in either order. We can also rearrange them. Sometimes my students will accidentally put the letters in different orders on different parts of their logic expressions, and they won't realize that those are equal to each other, and you can do something with that. So just keep an eye out for that. The next one is the same, but with OR gates. So x or y is the same as y or x. Again, it doesn't matter which order we apply that OR in, it still works. Number 12, same thing, but with kind of parentheses pairing. So x and the quantity y and z is equivalent to the quantity x and y ANDed with z. We can also do that in theorem 13. We can move where the parenthesis is with OR gates. So we have x or the quantity y or z, and that's equivalent to the quantity x or y ORed with z. And I hope you're paying attention to the specific way that I'm saying these out loud, because I'm trying to be very intentional with how I say these logic expressions out loud. I think that's really critical to understanding and doing these well. Okay, theorem 14 and 15 are a little bit different, and these are referred to as the distributive theorems. So again, these are kind of establishing which math rules translate over to Boolean algebra and which ones don't. So up until this point, we've seen that, for instance, x and x does not give us x squared. We saw that up here, right, with theorem number 3, x and x. If I did x times x in an algebra class, I'd get x squared. But in Boolean algebra, I only get x, because x ANDed with itself is just itself, right? So theorem 14 and 15 tell us that we can use another trick from math, and it actually translates over pretty well, and that is distributive property. So that tells me that I can take something like x and the quantity, y and z, and I'm going to use a word that we've used in math, even though it's not for Boolean algebra. I'm going to multiply out that x, or in this case, I'm going to distribute the ANDed x into each of these terms. So x will get distributed to the y term and to the z term. So if I rewrite that, you can see that I get x and y, or x and z. The x gets added to both terms. And I can do that with multi-term ORs as well when they're ANDed together. So theorem 15 says x or y and the quantity w or z. And we can factor that out just like you would in normal math, so the x and the w would go together, the x and the z would go together, the y and the w would go together, and the y and the z would go together. So if you put all those together, you get the exact expression that you see on the right side there, which is x and w, or x and z, or y and w, or y and z. So it works just the way that your typical math class would in terms of distributing. Now, one thing I do want to mention while I'm here is that we can apply these backwards. So oftentimes we will see logic expressions that have something like this. And it might be, theorem 14 I find is the most common, where we have a common term and we can pull that common term out. So I could apply theorem 14 in reverse and pull x out of the expression to simplify. And that's exactly what these logic expressions and theorems are all about, is helping us to simplify our logic so that it's easier for us to build these circuits, and at the end of the day, it's cheaper to produce because it uses less gates. Okay, so theorems 16, 17, 18, and 19, I'm not going to spend very much time on. These are pretty circumstantial, and the reasoning from where they come from is a bit convoluted, but the long story short is that these come from kind of hacking math, if you will. You're kind of adding a fake number that's there but doesn't matter. It's kind of like when you add 0 to both sides of a traditional math expression, or when you multiply both sides of a term by 1 to complete the square of a polynomial. That's essentially where these came from. What you need to know is that these are referred to as the consensus theorems, and these are helpful patterns that you can look for in your logic to try to simplify. So for instance, if I had something like theorem 16 here, where I had x or x naught and y, I could replace x or x naught and y with just x or y. And you might not see the benefit of that immediately, other than that it's a shorter term, but there's only one gate that's used in x or y. In the other expression, I have x or, there's one gate, x naught, there's another gate, and y, there's another gate. So I went from 3 gates down to 1 just by making that one substitution. So these can be very convenient in our simplification of logic expressions if we can spot that pattern. Okay, so hopefully that has helped, and I want to take a little bit of time to walk through some practice in how we do this. So I'm going to do 2 logic expressions in this video, and I'm going to show you how I want you to show your work. So the first logic expression that we're going to work on here is A and A naught and B, or B and C and C. So that is the beginning logic expression, and we'll call that F1. So what I'm going to do is I'm going to look at my rules for Boolean algebra, and I'm going to think about which one I could apply first to simplify this expression. So the first thing that I see is theorem 3. Theorem 3 says anything ANDed with itself is itself. And down here I have C and C. So I'm going to apply theorem 3 first. And it's worth mentioning that we can apply these theorems in a lot of different orders. It doesn't necessarily matter. Sometimes it makes things more complicated if we do them in a different order, but ultimately you should get the same answer if you're applying the same theorems to your simplification. So C and C is what I'm simplifying. So I'm just going to write over here theorem, THM, theorem 3, and I'm going to rewrite the expression. So this is now equal to A and A naught and B, or B and theorem 3 says x and x equals x. So I'm going to replace C and C in my expression with C. So that is the simplified form of the logic expression with that substitution. The next thing that I see that I have here is I have A and A naught in my expression, and I remember that I have a principle, or a theorem over here, theorem number 4, which says x and x naught equals 0. So x and x naught equals 0, and that was theorem number 4. So I'm going to write THM 4. I'm going to replace A and A naught with 0. So 0 and B, or B and C. Sometimes you're going to see that a 0 pops up, and you might be tempted to just start simplifying and not showing work. Please make sure that as we work through these logic expressions, that you show exactly which theorem you use to do each thing. For instance, you may have acknowledged that 0 and B is probably going to give 0, right? But make sure that you acknowledge that theorem in the next line. So let's do that now. So 0 and B, something's going to happen with that, right? So let's take a look at our expressions and our theorems, and we can see that the first theorem, theorem 1, says anything ANDed with 0 gives us 0. So 0 and B is going to be simplified by theorem 1, and that's just going to turn into 0, or B and C. So that's where we are now. Theorem 5 then says anything ORed with 0 is just itself. So we're going to replace this, theorem 5. Anything that is ORed with 0 is just itself. So the simplest way that we can write this expression is B and C. So I'm hoping that at this point you can see the benefit of Boolean algebra, because if we created a circuit for F1 here, I mean, I won't do the whole thing, but if we have A, B, and C, and remember that these dots represent my positive and my ground, my double pole, double throw, single pole, double throw switches, SPDTs, all of that is represented in this point, right? I mean, just for A, I'm going to have, you know, an inverter to make A naught, and then that A is going to come down here and AND with B. So I'll even use a 3-input AND and be kind of a bit of a cheater here. So that one's going to come down. These will come up here into this 3-input AND. Boom, 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 right? And then this is going to get ANDed with itself, which you can even see right there why that's a bit of a problem, right? And then that's going to go into an OR gate after that. So there's that circuit. You can see that's just a mess, right? Versus this circuit, which would just be, I don't even care about A anymore. I just have B and C, and they're going to go into an AND gate. And that's it, right? So this is super useful in simplifying circuits, making work easier, and at the end of the day, making things cheaper. Okay, let's do another one. This one's going to be a little bit more work. So x and the quantity x naught, or x and y. And we'll call this one F2. Okay. So the first thing that I'm going to do is I'm going to apply theorem 14 and distribute that x out. So let's go ahead and do that. So this will go with this, and this will go with this. I'll write theorem 14 here. So this becomes x and x naught. That's the first distribution. Or x and y. So hopefully right away you see that we have x and not x, and we just dealt with this a moment ago. So that's going to be a theorem 3 simplification. So I'll go ahead and write theorem 3 here. X and not x is 0. That's what theorem 3 says. So that's going to be 0, or x and y. Theorem 1, not theorem 1. Theorem 5 says anything ORed with a 0 is just itself. So now this simplifies to x and y. And then we've got one more step. We have x and x, right? And theorem number 3 says, oh, I used the wrong theorem. So just to clarify, the x and not x was theorem 4, not theorem 3. Theorem 3 is anything anded with itself is itself. So x and x is going to give us y. So that is theorem 3. So this simplifies to x and y. And we can't get any simpler than that. So, hopefully this gave you a good foundation to build your understanding of Boolean algebra. In the next video we'll talk about the last remaining theorems called De Morgan's theorems, which will apply to not and not or gates, and how we can simplify logic using those. So, I hope this was helpful. I'll see you in the next video.